thank you, Chushi, for the your introduction is very kind. I'm going to get started. So I'm going to stop the video. So in case there's a data flow problems. Um, Let me just see if I can get laser pointer. Okay. First, I want to just acknowledge the industry partners supported us developing these tools. So you know that when you want to develop a machine learning based tools or big data based applications, you want to work with a lot of utilities so you can get the actual data. You can see that we work with solar Strata Solar to get the PV data. And then we have electricity, so all these co-ops, they provided us with many smart meter data. I think in academia, it is very important to work with the industry to address their needs. And then also the realistic data set will make everything a lot more easier. We also thank the Department of Energy for their continuing support to our research. So today, I first will just briefly introduce our pathway towards developing machine learning-based algorithms. And then I'm going to give these audience with very little background in power system digital twin development, some background introduction. This will not be a complete or precise definition for digital twin, but at least it reflects our thinking in the area. And then I'm going to introduce the machine learning-based applications. You can see that we don't have enough time to cover every one of them. So I'm going to focus on synthetic data generation. We have done a lot of work in topology generation as well. I provided a link to it. You can see the YouTube video about this GAN-based topology generation. I have presented that 3 times before. So today I'm going to focus on the data generation part. And then I'm going to let Ian introduce the meta learning part. This is mainly the machine learning-based forecasting method. We have one for load forecasting, which we use a meta learning-based forecasting, and the other is for PV forecasting, which is TCM-based. Depending on how much time we have in the end, I'm going to introduce briefly about the reinforcement learning part work we do. So those are more on the control part. So synthetic data generation, and then forecasting, and then the control. Those are the 3 focus. You can see our group start to develop machine learning-based methods starting from 2017, where I got this first student from a computer science background. And then we developed a number of machine learning-based control method for controlling the battery storage device. And then our students start to realize that the machine learning will be a good technology that will be used in the future. And primarily, when you learn a lot of machine learning-based applications, you can find a higher paid job. So we have, you can see from 2017, only 1 student worked on that, and then slowly grow to 2, 3, and then the whole group more or less are doing some work in machine learning. So today I'm going to mainly focus on the GAN-based model, where we focus on generating the topology and then the feeder profiles, and then converting the low resolution data to high resolution data. And then Ian is going to focus on these 2. And then I'm going to present part of the work Si has done on the volt bar control. So these work we're still doing, you can check our publications to see works we have been doing in this area. First, I'm going to go over digital twin-based code simulation platform. We have been working in the past 5 years developing this digital twin-based simulation platform. So compared with the traditional power system simulation testbed, we summarize there are a few differences between that. First of all, the digital twin-based approach is highly scalable, and then it requires realisticness and then high fidelity. And then based on that, we can link this digital twin with the actual external controller, like selecting different responses or doing this real-time simulation, real-time situation awareness. So the thing is, when we do this digital twin-based method, the first, when we want to have a high fidelity test system, we need to have the model populated with synthetic data and topology so that it represents different system operation conditions. So we need automated parameterization compared with the traditional power system models. Usually they're snapshots, they're static, they can be updated based on the external sensor measurement. So the capability that you can update these parameters based on the actual data measurements, like the smart meter data or the PV farm data, is a great advance of technology. And then the other thing is the forecasting. So we want to provide a general purpose forecasting tool so that we can have the forecast for different energy management algorithm. For example, for home and building energy management, the forecasting is at individual load level. But if you want to control this resources on a macro grid, usually you have to provide transformer level or feeder level forecasting. And then if you want to aggregate them further to transmission level, you have to have several substations or regional load forecast. So if you want to have a digital twin, it's hard for you to connect the different specialized model together to the twin. It would be beneficial if you have a general purpose tool, for example, meta learning based tool, to give it a high level parameters. So it provided the modeling you need or the parameter you need to generate the forecast. So that way you can feed this forecast into your energy management tool to provide different type of response options. So this is another focus we have been doing to see if we can generalize the forecasting tool. And then when we have a lot of renewables in the system, we want to see if we can use TCN to capture the spatial and the temporal correlation. So these parts are going to be covered by AN. And the last part, once you have these digital twin-based approach, you can use reinforcement learning to develop control technology. Because reinforcement learning is like playing games. You need to simulate the game environment so the environment can tell you how well you performed, like the score, the reward, or how worse you performed. But the key is to develop a reinforcement learning based approach, you need an accurate simulation for the actual grid. So that's another motivation for us to develop a digital twin. So if you want more technical details, I compared the different type of test system with our digital twin based approach. And these are the publications about that. Since this tutorial is not about digital twin, so I'm only going to introduce this much. If you're interested in those algorithms, feel free to check our website for that. So these are the publications regarding the digital twin based approach. And then the next, I'm going to start to introduce the synthetic data generation method. So the motivation for us to carry out this study is when we started to develop these Parsons digital twins, we have very limited data sets. And then the data are usually collected in different places with different format. And then they have different data quality. For example, sometimes you have 1 minute data and sometimes you have 15 minutes data. So how can you switch the data from a low resolution, like 50 minutes, to 1 minute resolution? Can you do that even? So those are the motivation for us to do the low data super resolution and convert the low resolution data to high resolution data. And then a lot of the data also proprietary information. So they can only give you a few thousand, even though they have millions of smart meter data, but to academia, if you can have like 8,000 to say 20,000, that would be the maximum. And usually you only have a year or so, you wouldn't be able to have like 10 years. So based on that limited amount of data, how are we going to create the synthetic scenarios so that it can represent the different operation conditions and give us meaningful results? So that's the primary challenge we are facing. So we focused our GEM-based model, generated this synthetic data set, and 2 research front. One is generate synthetic topology representing the network structures, and the other is time series load and PV data. So those are the ones that I'm going to focus on. And then our research, all the work is generated from actual data sets, so we don't want to use synthetic data set to generate synthetic data. We want to make sure as much as possible to make this more transparent and then evaluate the realisticness of it. So the first method I'm going to introduce is load disaggregation. This is not really machine learning based, but we do have a HVAC load disaggregation. This is machine learning based approach. This is also an empirical method based approach. But load disaggregation is very important for digital twin development. This is because, first of all, in the past, I think for all of you who have done distribution planning study, you know that when you have a feeder head load profile where you can measure this, you have SCADA data, so you can have a feeder head load profile. But at each node, at transformer level or the house level, you really don't have that correspond to this feeder level profile, what would that profile will be. So in the future, when we have enough smart meter data, we probably can do that instead of using this disaggregation method. But a lot of the softwares is using the same load shape you measured at feeder head, and then they scale them down to different transformer. For example, if this is 50, then they have the same shape. It just have different magnitude. So as a result, for all these subsequent load nodes, you have same shape of load. So they at valley together, they peak together. So the results for this distribution study, the planning study, is highly questionable because the load actually is like this. At each node, you have different type of load profiles. And then also, if you have a building, if you want to do the demand response program, you also want to know what is HVAC, PV, and the EV charging load behind the meter. So your disaggregation not only disaggregate the load profile from a transformer level or feeder level down to each building level, but also for each building level, can you downscale and then disaggregate the major loads that used for demand response out. For example, this is a total load profile, and this would be the HVAC load profile we disaggregated, and then the green one would be the actual. So if you can do that, then you can estimate how much demand response result you have. So the first one I'm going to introduce is to how to disaggregate the load from the feeder level down to each load node. So there are two processes of it. The first one is selecting the load profile to be used from a smart meter database. And then the second one is allocate these load profiles down to each transformer. So I did an illustration. Think about a database. You have different shapes, and then you pull them out, and then form this possible shapes you want to use. And then you can have different transformers, and then depending on its rating, then you can assign these selected load profile to each transformer, so that they not only have the diversity, but they meet the local rating limitations. You want to have a load profile exceed the rating of 50 kVA, for example. So for this, we have three major processes. We took this from a load database, and then we try to match them to the feeder level profile. The first thing you want to do is select what are the points you want to have a precise fit, and then on which part of the curve you're going to have a relatively good fit, that will be okay. So this is our algorithm for this first part, the load profile selection. So I'm going to give you a step-by-step breakdown for how we do that. So first, we need to select the critical points, which capture the key load characteristic of load curve. So we pick the peak and the valley as the parts we absolutely want to have a fit. And then if this is one day, then we have a one pivot pair, meaning the peak and valley. If this is multiple days in a month, then you can select say 2, 3, 4, 5, 6 days to use their data pair as a fit. This is because you will not be able to have an exact match for this whole load profile. So it is important for you to understand for which part you want it to match exactly. And then for us to do that, we pick up the peak and valley. And the next thing is we want to maintain the load diversity. It means that we don't want to have all the load node have the same, exactly the same load shape as it did for the feeder type, feeder head measurement. For us to do that, we need a process to randomly give each node like 1, 2, 3, n. We randomly pull these loads and then populate it. So for the base part at each transformer, you have some randomness in there. So how many those curves need to be picked randomly? We have a band here. We call it the maximum p random. So we use this valley to control the peak of this random load selection. This is because we need to have this random load be in certain level. So when you're adding in the not randomly selected and more have this load shape as a gauge to select the rest of the loads, you wouldn't exceed this minimum point. So this random selection process guarantees us at each transformer, at least we have some load that are randomly selected from the smart meter database. So after that, we can have a residue load profile. Basically, you can have a P feeder minus the randomly selected load. Then this is a target feeder profile that represent the commonality of the profiles, because the reason you have this as a peak and this as a valley is because most of the load inside each transformer, when they add up, they peak here and then they have a valley around this area. So a simple way of doing that is simply just based on the target feeder the target profile, select another load profile peak at this period, and then have a valley around some area. And then the second one is more targeted selection. We use sort of like if there are two curves both peak at the same time, then which one we should select? We select based on the similarity, meaning we use the peak to select is here, and then our valley is here. Then we select a curve that have a closest shape, like the distance between peak and valley. That way we will guarantee that our selected curve will have a better characteristic overall to match the overall curve shapes. Instead of I have peak here, I have valley here, that kind of load profile definitely is not as good as the red one where we have the peak here and then we have valley there. And that's one way of doing that. So after this, we can see the other thing we can consider is the load composition. Because we have a large amount of smart meter database, this is got from the local utilities. Even though we only have about 20,000 load profiles, that already gave us a good mix for residential commercial loads. So when we construct this profile, we can also, based on your target load composition, say commercial load is 30% and then residential load 70%, to give your subsequent nodes a allocation so that the overall load composition will meet this requirement. And then you can see this is some example result. You can see that for weekly, we can actually do a comparison for selecting different pair, the pivot pairs, and then see which one provides you with a good match. This can be seen as a hyperparameter. You can select different pivots pairs. So in this case, even though you have 7 days, if you select 5 pivot pairs, you can get a close enough result. And then these are the parameters we use for evaluate how closely our generated aggregate curve matches the actual load profile at the feeder head. You can see that the pivot pairs, they do change. You can select 4 to 5 pairs for weekly. For monthly, it's not 30. It should be around 16 to 20. For yearly, you can select 36 pairs, and then you can match that, get a pretty good result. So I already listed the papers, detail the technical approach under each slide. So feel free to take a look at technical details if you're interested in it. So the next work I'm going to introduce is synthetic data generation. So in this case, we're trying to generate a group of diversified load profiles. Because if we want to only generate individual load profiles, we can use smart meter data. However, in our planning case, we usually need to generate correlated load profiles. For example, this particular transformer supply probably 3, 5, or 6 loads. If we only select randomly from a load database, 3 load profiles, they won't have the temporal correlation among this type of load because they are in the same area. They should have similar like square footage or user patterns. If you randomly select the loads from a database, it won't have this group level characteristic. So I gave an illustration for how different the algorithm is. If we use a single load GAN, basically we generate, we put smart meter data in, we generate a load profile to match the smart meter data. That would be it. It's like you put the cat's pictures in, and you can generate different cast pictures. As a result, you can have a load profile database. If you run this, for example, for n times, you will have n individual load profiles. And then you can randomly select, say, 5 or 10 of these load profiles to form a group. Then you probably draw these 6 different cats. But the way we want to do it is to have this group characteristics. For example, you want to generate a cat family with a mother with 4 kittens. If you do this, you will never be able to do that. So what we are trying to do is we put those profiles under the same transformer, and then we train that so that we generate those profiles. And then these are also the loads bearing the characteristic that's served by the same transformer or the same feeder or the same area. So this is the main idea for a multi-load GAN. So this paper we already submitted we recently submitted, it's just 2 weeks, so it's still under review, but we put the draft on the archive. You can download that for technical details. So for a single load GAN, you basically input only 1 time series data, you generate 1 time series data. So these convolution network is 1D. However, when we have a load profile, which you have like a group of load profile, one thing we need to do is we will have the profile to image encoding process, and then we move the convolution layer to 2D. So I'm going to detail the differences. So compared with the single load GAN profile, these are the major differences we have. So when we do the encoding and decoding, this is mainly to convert the time series data into an image. So we can directly use the algorithm developing image processing in our domain. So to gain enough resolution, we actually encode the load profile into 3 colors, RGB. So you can see that for different load levels, we can encode them into the red. And then at between 2 to 4, you can do green. And then above that, you can about 6, you can just 4 to 6, you can just do red. So that way we use 3 colors representing different power intensity. And then we added the 4th layer, which is the temperature. So the temperature also encoded into the 4th layer. So that's the profile to image encoding process, allow us to directly use the tools developing image processing domain in our domain. But what's the unique challenge in the group GAN generation? So if you look at these, it's hard for you to tell which one is realistic and which one is not. This is because you have to have enough expertise in power grid operation to recognize that. And also, even for an experienced engineer, it's hard for them to see by glance which one is true and which one is not, especially if you have a group of load, you also need to capture the group load characteristics. So the innovation we have done is to be able to letting the machine tells us which one is possibly the load profile under the same transformer, which one is not. So what we have done is beside this statistical evaluation, meaning we do statistical evaluation for the load serving under one transformer to see their peak load distribution, mean power distribution, load ramps, and hourly thing, and then to compare all these characteristics to see if they are under the same transformer. We also train these specialized classifier to achieve this same purpose. So for us to do that, we need to create positive samples, which we have. This is the label data set from the utility. They gave us, okay, here's the transformers. Here's the loads serving under same transformer. So those are labeled data set. However, what we don't have is negative samples. we cannot directly tell that what is negative sample. You can't simply pull, say, 5 load profile from a different transformer and then claim it to be negative, because in distribution system, especially for an area, say you can have a system where you can have 8 customers supplied by transformer A, and then 8 customers supplied by transformer B. So this is a transformer, you can have 8 customers here, and then this is another transformer adjacent to it, have another 8 customer. However, for this customer, it could have been supplied by this transformer A instead of 2 is equally likely, especially for smaller loads. It can be happened supplying by different transformers. So if you use a randomly draw profile, claim it to be negative sample, that won't work in this case. So we spend a lot of time trying to find out what is an effective way to generate negative samples. So that way we can train a specialized classifier. It can tell us, instead of letting a human or an engineer standing there to tell us for generated load profiles, are they the loads under the same transformer or not? A second. Okay. So this is the overall process for us to do the data augmentation, because even utility gave us a lot of data, but compared with the actual data needed for training a GAN-based model, it is not that many. For example, we have 10 or 15 transformers, and then under this we have 8 loads, and then we have 3 years of data to train that. But to have a more reliable model, we need more positive samples to train our GAN-based model. So in order for us to do that, we actually have a data augmentation process. What we have done is that we pull the load profile from the smart meter data file. So we have about say 10,000 or even more smart meter data here. We randomly pull them from the smart meter load database, and then we use our trained classifier, and then tell us whether or not this randomly draw the new group of load profile, it is served under one transformer or not. So we select these with a very high confidence to be a positive sample. So this positive sample, together with the original utility given labeled data sets, we can train the multi-GAN based model. Also, we can use this after this one is pre-trained. We can use this to generate a group of load, and also feed this through the classifier to select these highly positive samples. Use that to augment the original training sample. So this is the augmentation process for the multi-load GAN. And then the other augmentation process happens in training the classifier. So what we can do is that we have the original positive sample again from the utility label data. So these are the ground truth. But using that only may not give us enough training data. So we use the multi-load GAN and randomly generated to have these augmented positive samples. The difference between this highly confident and then this augmented positive samples is because this one is like 0.9 and this is 0.5. So this is to give us more flexibility to train this deep learning classifier. And then for the negative samples, we use a process. We can use different kinds of statistics to see whether or not the generated one will definitely not be a positive sample, so that we claim that to be the negative sample here. And then also the other one generated by multi-load GAN and by the randomly selection process, if the confidence level is very low, then we use these as negative samples. So you can see that these two training process actually is coupled together. So if you only train one at a time, then the result won't be satisfactory. So as a result, we train these two processes iteratively. So we train our classifier. When classifier gets a new data set, we will new parameter, we update this process. So the multi-load GAN and then the classifier training is combined together, iteratively train that. By doing that, you can see these are the results we have. without doing this multi-load gun model, you can see that this single load gun will have a distribution like this. So the real one is highlighted by the green, and then the multi-load gun is highlighted by the blue. So this is without augmentation. You can see that the distribution of the generated multi-load gun model is definitely better than the single load gun. You can see the single load gun has a very different distribution, but compared with the real distribution, you have less data sets in this low score area. So with the data augmentation, we can force this two distribution to be closer. So it means that it's more closer distributed compared with the actual data set. So the augmentation part make this data more realistic. So I'm going to spend a little bit of time just to talk about the topology generation. So the more detailed explanation, you can scan this QR code. And then there's another presentation for that. I think Ming also made a short presentation about the feeder gun. The focus of my presentation is just to give you the general thinking when you use gun-based model for synthetic data generation. What's the commonality for the data and topology generation? What's the different considerations? So you can see that when you generate the topology, it's very different from generating the data, because you're generating, basically, these are your inputs. Your inputs are graphs. So we took the actual feeder topology. We have to represent them into graph representation, like adjacency matrix. And then we start to generate these different feeder profiles. So the unique consideration of that would be, instead of counting the geographical distance, we actually use electrical distance, meaning it doesn't matter when we generate topology what the geographical consideration is, like how this curve go this way or go that way. We only need to know the distance between this nodes to this node and to this node electrically. So we can straight the lines and then just get the connections correct. That will be it. So this is one consideration you want to do. And the second is in our power system modeling, we use device as a node. But in this graph theory, usually you have to change your view. So for our conductor materials, these are actually the nodal attributes. So each of these nodes in graph, they represent a line like conductor and then their characteristics. So this is very different from our power flow computing. You have this as a bus voltage, and this power flow is the impedance or things like that. So those are different considerations. So after we have this two simplification, we use electrical distance, and then we use device as a node. Then we could convert them into a graph, and then we can use that to train the gun-based model, and then trying to use this gun to generate these wheel graph. It's similar to image generation process. So you can see that this also faces a data scarcity problem, as what we have done in the smart meter data generation. Because for us, we can only probably get, say, 14 real feeders. They are similar type residential feeders, and then you can have nodes from 5000 to 2000. So we need more graph to learn this topology and attributes. So one thing that we did is sample subgraphs, because for these feeders, you have many subgraphs that can equally likely occur in other areas. This is the unique to our power grid, especially power distribution grid, because your transformer is 50 kVA. On this feeder, on that feeder, your connection for these transformers are similar because they follow similar design rules. So that way, if you get a subgraph, it's equally likely making sense. So by randomly sample that from this whole graph, we can get a lot more graphs than this originally the whole graph would have been. So this way we can successfully enlarge our training data. So this data scarcity problem exists in both the synthetic data and topology generation process. I think it's a very important in our application, trying to see what is a proper way to generate augment data and whether or not that makes sense. So for the other thing is for both case is how we evaluate the realisticness of it. So you have to have attributes. Later on, you can use these attributes trying to decide whether or not you have the same attributes as a real feeder would have been to assess whether or not a generated set of topology is actually realistic. So you can see that we select the length and then amps and then this different type of attributes in this system. And then later on, when we have this whole thing work, we find that one more steps that we need to do, which is post-processing. You can see that later on when I introduce the other GAN-based model, the fine-tuning process is much needed. This is because if we do this, we can see that if we let this GAN-based model run uncontrolled, in the end, they will converge to a view graph like this. So they wouldn't have the diversity of this graph like a real feeder would have done. They converge to a very narrow range of graph. This is the mode due to the mode collapse. So there are two things you can do for that. First, you can do a feasibility check when you use PowerFlow to run this feeder to see if you have reasonable voltage profiles or if it is solvable. So this is using its physical characteristic to see if your generated topology actually works. And then you can also do post process screening using these kind of characteristic. For example, you have a three-phase feeder like ABC for these segments. So following the ABC segment, you can have A, B, C, A, B, A, C, B, C, A, and B, C. But to follow BC, you can only have BC, B, and C. You cannot have a segment in phase A. So using these characteristics, you can exclude these topologies that are physically violate the connection characteristic a real physical system would have done. And then we can also test on our generation the feeder, how many of them are A, B, A, B, C, and then for these distribution, are they similar to the actual feeder would tell us. So this way we will generate the view graph, have the same ABC component, the same length, and then the ratings. So the last part I want to introduce is the one that should be presented by Li Dong because he's not here, so I will present on his behalf. So the super resolution, the motivation for that is mainly because we normally have these loads that are giving us a different data resolution. For example, we can have 15 minutes data, and then we can have 1 minute data. Depending on where the data is from, you can have a very different resolution. So suppose we have a set of data, we have both 1 minute and 15 minutes data. How can we actually using this building a training algorithm to let the GAN-based model use 15 minutes to generate 1 minute data, and then use this data set, we already have 1 minute data as a training data set to see how far generated the 1 minute data, how close they are to the actual. So this is our original thinking of it. So this is the basic GAN-based model. Again, you have a generator generate these profiles. And then you have the real data profile, and then you can compare the real with the fake to see how close they are, and then using the difference to drive the training of a generator. So this is motivated from the image processing algorithm, where we can have a blurred image, and then using the super resolution algorithm, we can recover the details for this image. Similarly, if we have 15 minutes data, we can recover the 1 minute or even faster variations of the load profile. So these are some examples. So this is our 1 minute data, this is 5 minutes data, this is 15, this is 30 minutes data. You can see that for different resolution, you lose these process dynamics. So those are the details you want to recover. So by doing that, the unique consideration that we have, similarly to all the other GAN-based model, is how you design your loss functions. So you can see that these content loss are similar in the image domain. So we make no innovation in this aspect. And then you can use adversary loss, which you use the generator and discriminator losses to drive the operation. this is also a fundamental aspect from the GAN-based model. So when you use this in power domain, you basically didn't make a lot of contribution in these two parameters, loss terms. So the third one, we have, I think this is some innovation, because what we are doing is we took the higher level layer features, we compared this feature difference, and then use that as a way to drive how close they are. Some of these image domain applications also use some of these higher level feature consideration. So this is new, but it's not that new. But a lot of these ones, I think, will be actually more effective by including this feature, because this is a level of feature that we humans cannot see from our eyes. These are many hidden features in the higher level. They already get to the convolution data, and then you convolute a few layers, and then you get a higher level feature. Usually are not the features that you can simply observe by eyes. So these comparison adding here will improve the performance significantly. So here's the part, like I said, in the topology part, the polishing network is important. We're using the power system knowledge to see whether or not some of these generated data require some fine tuning. It's almost like you generate a figure like that. Only a few parts are not really good. If you can fine tune those details, then it become a good result. So this is where you do the polishing. So for polishing network, we took the output from the GAN-based network, and then we do these kind of polishing. This is the before polishing, this is the after polishing. We have, again, this polishing network also need to design the loss function, which you drive this different aspect you want to preserve. The first is the shape-based loss function. Basically, we want to have the outline here similar to the ground truth. So by doing that, we want to calculate the local peaks and valleys, so that here and here the differences are not that big, and then also the shape follows the similar shape as ground truth. So you can see before polishing, you can have a lot of spikes here, but after polishing, based on the ground truth, we can actually guide these errors to be down. Similarly, you can get to the change of load, which is mainly the ramps, to avoid the high ramps, which would never occur in reality. So these are the polishing part. You can also, based on your different knowledge, to adding in more loss terms, so that these two will be matching more before the palette than the curve you obtained before polishing. So next, I'm going to let Yi-Yan start to give you switch a topic, because you can see that I presented mainly GAN-based method. So now I will let Yi-Yan present the forecasting method. Hey, Yi-Yan, can you please take over from here?
Yeah, sure. So okay. Thank you for the introduction of Qiushi and Dr. Lu. So before I get started, I think there is a question for you, Dr. Lu, in the chat box. So I wonder if you wish to answer it right now or put it
maybe we can let people put Q&A on the chat box, so we can answer that all together.
Okay, sure. So can you see the slide? Right? I should.
Yeah, we can see it, but yeah, we can see it. Go ahead.
Okay. So as Dr. Lu mentioned, today I will mainly present some forecasting methods, so including a load forecasting method and a PV forecasting method. So this is the role the forecasting methods in the whole framework. So basically, it belongs to the field of situational awareness. The situational awareness means we will use some machine learning or data analytics to try to monitor the current status of the system, and we will also forecast the future of the system, and also we will detect some anomalies. So today, the main approach I use include the meta learning for load forecasting, and another one is the temporal convolutional network for PV forecasting. So first is the meta-learning based load forecasting method. So this is a brief introduction about the meta-learning concept. So briefly speaking, the meta-learning is more of a cross-task technology. So here we firstly define what a task means. So for example, this is an image classification task. We will develop a classification model, we call it F1, to try to distinguish between the image of cats and the image of dogs. So in order to do that, we will have some training set with cat and dogs labeled. And then after we train the model, we will implement them to the testing side to achieve the classification for cats and dogs. So similarly, in our load forecasting area, we will also have a training set to train our model. And also, after the model is trained, we will use it to predict into the future. So this is called a single task. It's a single image classification task and a single load forecasting task. But in reality, we will always face multiple different tasks. For example, here we still have the cat and the dog classification. We call it task 1. But we also have another different classification problem, which is the apple and orange classification. It is called task 2. And but now we will have a new task. Let's say we will need to classify bikes and cars. So we haven't done this before, and maybe we do not have much samples to train a model. So in this case, how we define that what kind of classifier we should use? We should use F1 or F2 or a brandly new one. So this is where the meta-learning concept will work. So basically, the meta-learning will learn from the previous task 1 and task 2, and based on the experience of solving the task 1 and the task 2, we can learn some common knowledge of handling the classification task, and then give a model recommendation to solve the new task. So for example, here, based on meta-learning, the meta-learning will recommend the F1 as the solution to the new task. So we will use F1. So the reason we do this is that when we face a new task and we do not know which model to use, if we have a recommendation system like this, we can save a lot of time because we do not need to test every model one by one, right? And then we can have a better accuracy to eliminate some large errors. So this concept can be used to the load forecasting area. Because similarly, we will also have a lot of different load forecasting problems with different forecasting requirements and different data conditions. And then after solving a certain number of load forecasting problems, we can use the experience to guide our next step to solve a new forecasting problem. So this, in this way, we can also save some time and improve our accuracy. The reason we need it, as I mentioned, because we have a lot of heterogeneous load forecasting problems, especially in the power distribution system. So for example, we will have load forecasting problems with different load level. Sometimes we need to forecast the load for a single user to support the house energy management. And sometimes we need to forecast the transformer or microgrid. And sometimes we need to forecast the substation or the whole city. So this is only one dimension, meaning we will have quite a different forecasting requirement and data characteristics. So for the data granularity, we will also have pretty different situations like 15 minutes, 1 hour, daily or monthly. So all these dimensions, if you combine them together, we will have a lot of different forecasting scenarios. So here is, for example, if this is an example of a single user forecasting, we will probably need to forecast the load for this house for the next few days or hours. So all of these forecasting problems are pretty different in data condition and forecasting requirement. So as a result, we cannot solve them by any single forecasting model because different model has different pros and cons, right? So what we need to do is to select the most proper model for different tasks. So every problem can be solved by the best solution, so the accuracy can be improved. So in order to achieve the model selection for different load forecasting problems, here is our technical flowchart. So because this paper has been published and we have presented it once before, so here I won't dive into too much details. So this is our publication, and we also have a YouTube video to introduce it. If you are interested, you can take a look. And this is a brief summary of the key results. So basically, we prepared 10 candidate models and try to solve up over 800 different load forecasting problems. So we can, by the time we make the publication, we can achieve like 64% accuracy to hit the best load forecasting model among the 10 candidate models. So that means if you randomly select a model to solve a load forecasting problem among the 10 candidates, you have like a 10% chance to hit the best one, right? So, but right now we improve it to 46 by the time we make the publication. But after we make some fine tunings of the meta learning model, right now we can achieve over 70% accuracy to hit the best one among the 10 candidates. So because we can always identify the most effective forecasting model, so the error ratio is significantly reduced. This is the average error ratio among the 800 forecasting problem. So in summary, this is mainly a load forecasting model selection framework to handle the heterogeneous load forecasting problem in the distribution system. So if you are interested in details, you can take a look at our paper. So the next is the spatial temporal PV forecasting. So this is more of a hybrid PV forecasting framework, including both the data-driven model and the physics-based model. And we will also put some domain knowledge into the whole framework to improve its performance. So the physics-based model means we will firstly build the model for the PV farm, mainly including the PV panels and the modules and the inverters, so that we can achieve the conversion from irradiance to power. So in this way, once we get the irradiance prediction from the national weather agencies, then we can convert the weather prediction into the power prediction. So based on the physics-based model, we basically make a conversion from the irradiance to power. We do not provide any forecasts from ourselves. So theoretically speaking, if the physics-based model is perfect, then the forecasting error mainly comes from the weather forecast. So this is like a weekly ahead forecasting results from the physics-based model. So the advantage is that it can provide a pretty long forecasting horizon, like up to a few weeks, because we have the support of the numerical weather prediction. And the weather prediction can be up to a few weeks ahead. So this is the advantage. We can look pretty far away. But the problem is that we cannot capture the intra-hour fluctuations. This is because usually the NWP is in hourly basis, and it will be pretty expensive if you want to get some intra-hour predictions from NWP. So in order to capture the fluctuations within each hourly interval, so we introduced the data-driven spatial temporal forecasting model to provide more details. So this is what the data-driven model forecasting results will look like. So basically, you can see that it can provide the pretty granular forecasting results and capture the intra-hour fluctuations. as long as you have a pretty granular historical data to train the model. So, but the problem of the data-driven model is that it only has a limited forecasting horizon. Because, for example, it can only look into the future like 6 hours ahead at most. Because without the support of the NWP, the data-driven model cannot know what the future weather condition will look like. Will it be cloudy, or be sunny, or be rainy? It can hardly be predicted based on the historical data, because the weather changes pretty fast, right? So briefly speaking, both the physics-based model and the data-driven model, they both have their advantages and disadvantages. So here's the question. So can we combine them together to get a more powerful forecasting tool? So that's what we are trying to do in this work. So this is the technical flow chart of this work. So in the first half, highlighted in orange, basically this is the physics-based part, which provided the days ahead forecasting. So basically we use this model to capture the trend of the power fluctuation with hourly granularity. So more specifically, we will firstly have the NWP as the input. And before we feed the NWP into the physical model, we will firstly use a temporal convolutional network to blend the NWP results from different data sources. This is because we think different NWP has different data source has different pros and cons. So after blending them together, we can further improve the performance. So after we blend the result NWP, and the blended result will go through the physics-based model to generate the trend forecasting for the next few days. So this is what it looks like. It's pretty, it's not it's in hourly basis, so it's not very granular. And on the other hand, we will derive the data-driven model. So the data-driven model is basically to capture the spatial temporal correlations among the target site and its neighbors. So for example, this is the over 100 PV farm in NC State, and this is our target site to predict. And then firstly, we will code them into a data matrix, and the target one is the blue one. And next, we will select the most correlated neighbors for the target site. And then we will, after we made the neighbor selection, we will feed the data matrix into the TC model again to achieve the forecasting. So this is like, because our historical data is 5 minutes, so our forecast is also 5 minutes. So this is a more granular result. So finally, we will both have the physics-based model results and the data-driven model results. So they could be pretty different from each other. So here we will use TC again to reconcile the day ahead forecasting results and the hours ahead forecasting results to get the final forecasting results. So after reconciliation, we expect that the final results can both have an accurate trend term and an accurate fluctuation term. So the results can be further improved. So next, I will introduce a few technical details for this framework. So the first key algorithm is the temporal convolutional networks. So this is the main structure of the network. So there are two distinguished features for this network. First thing is the dilated convolution. You can see that after a few layers dilation, so there are some empty blocks, and we will skip these empty blocks. But because of the dilation structure, we can have a pretty long receptive field with limited complexity. Because we do not calculate the parameters for every block, we will skip some unimportant ones. And the second feature is the causal structure, meaning it only leverages the information in the history, and there is no leakage, information leakage from the future. So this makes it suitable for a forecasting problem. So in our work, we will implement the TCN in 3 aspects, as I mentioned in this framework. So firstly, we will use TCN to blend the NWP data from different NWP data sources to improve the weather prediction accuracy. The second implementation is the spatial temporal forecasting, as I mentioned here. We will use this network to extract the spatial temporal correlations among the target and the detector sites. And finally, we will use this framework to, in the sequence-to-sequence mode to achieve the forecasting reconciliation. So the second key algorithm is the neighbor selection algorithm to identify the most contributing neighbor. The reason we make the neighbor selection is that if we directly put all the data into the machine learning model, then it will make the model training pretty time costly and make it pretty make the machine learning task pretty difficult, because we have too many redundancy informations that are not relevant to our purpose. So so in order to make the target site detection, so the first thing we have done is to define a successful detection rate for a detector site. So this is how we do it. Firstly, we will extract the cloud events from historical data. So for example, this is the 1-day PV profile, and we will only keep the large power drops. And this is because these drops are caused by cloud movement, and these drops are the most critical ones we need to predict. And after we extract the cloud event from both the target site and the detector site, we will calculate their time lag, the correlation coefficient, meaning we will find the optimal time shift that can lead to the maximum correlation among the detector and the target site. So, and finally, we define a successful detection when the time shift is larger than 0 and smaller than a certain threshold, meaning that the cloud event will be firstly detected by the detector site, and then it will go through the target site. Only in this condition, the detector site can achieve the prediction effect for the target site. On the other hand, if the cloud firstly goes through the target site, then the detector will no longer work, right? And then based on such definition, we also define successful detection rate, meaning among all the 6 possible scenarios, how many scenarios are successful detection. And then the higher the successful detection rate means the more correlated the target, the detector site, and meaning it is a better choice to formulate a detector network. And then in order to select the optimal detector site combination, you know, it's an NP-hard problem. There are endless possibility of combinations. So here we developed a greedy search algorithm to automatically identify the optimal detector site combination. So based on our algorithm, we do not need to any human intervention to the algorithm, and it can automatically tell you, okay, these are the optimal detector site combinations that can lead to the maximum successful detection rate. So for example, in the first case, we have 7 detector sites selected, which can maximize the detection rate. And then the key algorithm 3 is the reconciliation. So we will still use the TCN model in the sequence-to-sequence mode to reconcile the day-ahead forecasting results and the hours-ahead forecasting results, and to obtain the final forecasting results. So this next, I will briefly go over some case study results. So firstly, for the physics-based model, we tested its accuracy by feeding field measurement data into the model. So here you can see that after the model receives the actual data, it can generate very accurate output. Yeah, the blue one is the actual one, and the green orange one is the simulation. They are very close with an error less than 1%. So that means the physics-based model itself is pretty accurate. The forecasting error only comes from the NWP. Then we will feed the NWP into the model, and you can see this is the forecasting results compared with the real results. So we can roughly capture the trend of the forecast of the power output, but we will fail to capture some intra-hour fluctuations. And next is the case study for the data-driven model. So firstly, we do the 1 hour ahead forecasting to prove the effectiveness of neighbor selection strategy and the TCN model. So, we propose the neighbor selection TCN, we need to demonstrate it's pretty effective, right, compared with the existing methods. So we tested the algorithm on 95 PV sites in NC State for 1 hour ahead forecasting. And we defined 4 different neighbor selection scenarios. For example, the first one is our proposed neighbor selection strategy. The second one is the case without any neighbor, meaning we only use the historical data of the target set itself. And then the third case is all neighbor cases. We do not make any selection. We just directly put all neighbors into the forecasting model. And then the last one is the random neighbor, meaning we still select some neighbors, but there is no selection strategy. We just randomly select some neighbors and put them into the machine learning model. So you can see that based on our neighbor selection strategy, the performance and the RMS is the smallest, meaning the neighbor selection is effective and necessary. And in this case, we also tested 4 different forecasting algorithms, including our TCN and another 3 pretty advanced deep learning model. We can see that the TCN model is relatively has the better performance. So next, we will give a more comprehensive test on the data-driven model, because here we only test for 1 hour forecast. Here we tested for varying length forecast horizon. So here the forecast horizon will vary from 5 minutes ahead to 6 hours ahead. And this is the error performance. We can see that the TCN model combined with the neighbor selection strategy has the best performance and also the best computation efficiency. So finally is the result reconciliation. So briefly speaking, this the blue band is the forecasting results among the 95 PV sites before reconciliation from the data-driven model. You can see that after 2 hours, the forecasting error will increase significantly. But after we reconcile the forecasting results between the data-driven model and the physics-based model, the forecasting error can be significantly reduced, especially after 2 hours. This is mainly because with the guidance of the day-ahead forecast, because the day-ahead is supported by NWP. So once we incorporate the day-ahead results into the real-time results, we can have a better trend forecasting result. So the accuracy can be improved. So this will be my presentation for the 2 forecasting model, including the meta learning-based load forecasting model selection and the hybrid PV forecasting model. So Dr. Lu, would you like to take over and introduce the last part?
Sure.
Okay.
Yeah, I have answered some of the questions already in the chat box. If you have any question for Ian and me, you can just keep on typing that. So I'm going to wrap it up in 5 minutes. Here, I talk about the last piece of algorithm that I want to introduce briefly is the reinforcement learning based load-to-hour control. So here, what we did differently compared with oops, sorry about that. Compared with the state-of-art approach is the two-stage training we proposed. The way we want to do that is because reinforcement learning is notorious for having the conversion problem. if you have in the future tens of PV farms in the system, all performing both fire control, you train them together, it's very hard to converge. So what we have proposed differently in this paper, which is recently published on the general meeting, is the two-stage training. So in the first training, we will assume all other PV agents are not acting, and then we only let one PV to regulate the voltage. So through this training, the PV will learn when to take an action to handle the voltage problem in the system. And then in the second stage training, all these PVs are already pre-trained. So they already know when to act and when to not act. So the second stage will be focusing on the cooperation to let them know how much they need to contribute in the presence of other PV farms in the same system. So by this idea, we have, first of all, in the first stage, we focus on designing this different stage, because all we want to do is not exactly how much you need to contribute, but to see what are the basic strategy you need to take. You can either do nothing, meaning we don't do anything if there's only a slight voltage violation or the voltage within the zone. And then we have absorbing and generating. So when we have a low voltage, then we will start to generate bar. If we have high voltage, we start to consume bar. So that's the basic thing we want to learn. The unique consideration for us in this case is to introduce a do nothing strategy, because not every action is useful. And then we also put a cost for taking action. So this way you would make sure that the agent's action are stable, so it won't oscillate between absorbing and generating. And then the second stage, when we do the cooperative training, we focus on how to distribute the award to each agent, to award these agents with the most contribution that can reduce the bar, to reduce the over voltage or under voltage the most. So you contribute, your contribution is actually the base for decide how many award you can get. So this is more what I think is unique, because we're developing a journal paper for that, and I won't get into too much technical details for the work that we haven't published yet. So I'm going to wrap up this tutorial by having this digital twin-based approach. Basically, we don't need to conduct the field test, but because of that, if we want to use digital twins to replace the field test, we need it to be highly realistic and scalable, so that you can do all kinds of tests from on a house level, building level, feeder level to the whole system level. So this model needs to be scalable and be able to change these parameters on the fly to create different operation conditions. So if we want to do that, we need to use machine learning basically help us do the following. First of all, how we can guarantee its high fidelity. Since we only have a small amount of data set to start with, how we can augment the data so that we can make the result representative, especially to represent not only the normal operation conditions, but also the rarely occurred conditions, to have a balance in the data set. And then we want to make sure that we know what is realistic, what is not. In image processing domain, you usually can say, hey, this is a real cat, it looks like that. You cannot do visual inspection because in power system domain, it's hard for even an expert to tell a load curve or a topology to be fake or real. So we need to have a more delicate way to evaluate the realisticness of generated topology and data set. And then the next thing is explainable, repeatable, and replicable. These are the general considerations for nowadays machine learning applications, especially in power system domain. If we cannot demonstrate our data is high fidelity and then it covers the wide range of operation conditions, we cannot let operators use a digital twin to replace their current field test. And then also we need to allow humans to interact with it. And then to see how we can actually let our modeler to interface with a digital twin to change the setting. And then we need to eliminate the data set, the bias of it, especially when we have a data set from one geographical area representing one type of a demographical distribution. how we can use that in other areas with a different mean temperature, for example, or the age group or income levels. And then the other thing is cybersecurity considerations when we generate synthetic data sets, how we make sure that the data we have cannot be backtraced to the actual data sets that will damage the security of these actual data sets. The other thing is for this community, we said we need to really open source to accelerate development. Otherwise, we wouldn't be able to check the data sets, how realistic it is there any bugs in the system or things like that. If we all share data or the algorithms together, probably as a group, as society, we can develop the machine learning based method much faster. Okay, so I'm going to just keep the tutorial as this far, and then we can go to the Q&A session. Qiushi, you want to start that?
I will take over. This is Yang from Arizona State. Yes, thank you, Professor Lulin, about this wonderful talk. I will start with part one. So in part one, you talk about load disaggregation. So one question that I received was, do you need three-phase voltage current data? People, the audience ask, since the three phases are mostly unbalanced.
Oh, yes. We actually did that as three phase. What we are doing is for distribution system. I should emphasize that our work, all of them are actually for a distribution system. Our feeder is three-phase load. So we do have A phase, B phase, C phase, right? So that balance can be maintained. Actually, in Jiu's paper, he mentioned that. I just didn't present it here. It's similarly to how you control the residential load and commercial load ratio. So you can control for each phase, like A, B, C phase, and then how much load you're allocating there. But the main control for this number of loads is transformer capacity, right? So what we have done, what I didn't mention here is for larger transformer, usually if it's three phase, then we allocate the three phase commercial load on that transformer first. Because the large load would definitely won't be allocated to a small 50 kVA loads, right? So we do consider that as well. There's a sequence. We will allocate these large commercial loads to the large transformer. That way we would be able to consider not only the phase balance, but also the commercial load and residential load, and how realistic for a large load to be on a transformer. Yeah.
All right, that's very nice answer. And the same audience was asking, in distribution system, the data can be bad. So if they are missing data in one location, how are you handling that?
The missing data to us, if you're thinking of the GAN-based model, it's not a big deal. Because what we have is we have 8,000 smart meter data from one utility, right? We have like 300 from this utility. We have maybe 800 from another utility. So for a missing data in this area, you really don't make a significant difference. You can just throw them away most of the time, right? So for the load disaggregation, that problem, usually when we have a large database, we actually use already processed smart meter data, meaning for our smart meter database, all the missing data already been excluded. We would just use those with complete data set to generate to do this, because you only need 1 week, right? If you have like another week that has bad data, you simply just throw them away. You don't want to patch them because it creates bias. So if you have enough data sets, the easiest thing you want to do is just throw them away. Yeah. Okay,
that's very good. And then it's going to the second part. In the second part of your part one, you talk about the super resolution. So last time you mentioned super resolution in the talk, and many people feel very excited. Even my student was talking to me about how to do super resolution. So there's one question from the audience. The question is, when we look into the low resolution data, we typically cannot increase the resolution because there's a Nyquist law, right? So you need to sample higher in order to recover the original one. So now you show impossible is possible, but is there any key or
Yeah, the key is you need to have a high resolution data to start with, right? So what we have done is we have PCONS3 data, which is 1 minute data, right? So our algorithm basically can be developed using that data set. And then we have already the high resolution data. We downsample them to 50 minutes, right? So those are the training data set, and then you can use that, and then you can develop the super resolution algorithm. But the drawback of this is when you transfer your model from this data sets to another, for example, we use them directly in NC, North Carolina area. Texas and North Carolina does have a difference in temperature, right? So you would create some problems in this process. So if you can have like say 1 minute data in North Carolina area, and then use that to fine tune this model, it will be better, right? But what my point is, as long as you have 1 minute data to start with, you can develop an initial pre-trained model. And then when you use it in another area, for example, if I want to do this in this area, I would work with my industry partners. Let them do a particular sample period for like say a month, getting the 1 minute data, because I talked with the utilities, and then it is possible for them to sample at 1 minute interval. But they don't want to do that because this will take a lot of storage room, and then there's no necessity for them to do that, right? But if you talk with them saying, okay, well, I only need about 1 month's data to use that to fine tune your model, and then the rest of it would be okay, right? So that is possible, meaning as long as you can have a high resolution data and then a low resolution data, a pair for the training, you usually can achieve this. This is been proved by this study already. It's just in reality, in realistically speaking, if we do this, move this model using transfer learning to other area, can we still use the same model parameter for that, right?
All right, that's very nice explanation. The audience, Sharon Wang, had a question. How about the switching operations, the load movement between the feeders? Sorry, this is a private message to me. Sure. Professor Lin Lu, do you know which part it is talking about, or do you need Sharon Wang to unmute and clarify? Let me repeat. How about the switching operations, the load movement between feeders?
The switching movement of the load from feeders. Is this which part of this is about?
Right. Okay.
For
yeah.
the topology generation, or for which part?
Right.
Can you clarify that?
Right. Can you unmute and clarify?
Is she online?
Yeah, she's online.
Okay.
Oh, okay. Oh, she said her microphone is not working.
Oh,
Then
okay.
can you try to maybe do the scenario if it's part A, then what's sorry if it's part 3?
Yeah, is it about topology generation, or is it about the load disaggregation, or this is about the mode bar control?
Right, let's see whether Sharon can type.
Yeah, I don't think this is related with the EN's part, because that's the PV stuff, right? So
okay, while we are waiting,
yeah,
while we are waiting for Sharon to type which part Sharon is talking about, I can get another question. The question is from Saga Zigai. The question is, what are the assumptions here about electrical system, as there are multiple variables in the system? I guess there is a need for clarification again. So Saga, do you mind to unmute yourself to elaborate which part you are talking about? I will ask him to unmute.
Can you repeat the question? So I will try to see if I can.
Yeah.
Or
So,
I can just answer the other question. I think Matthew asked the question, which is a very good question. Even though I tapped that on the chat box, I think it's worth of just a clarification. So Matt asked me about this, this because we generated topology, right? Topology is a network connection. That's what we generated. So Matt's question is about how you are going to finish this by having the load, the capacitors, the transformers in there, right? So when we generate topology, remember we have the nodal attributes, which is the line, like how the line is, and then or the nodes will have a capacity there. So these can decide the transformer capacity. So once the transformer capacity is determined, we can use load disaggregation method to allocate the load profiles to that transformer. So once you have the transformer capacity decided, and then the number of customers allocate to there, you will have a load profile, right? Then you can run the power flow studies to decide what part you need a capacitor bank, or whether or not you need it at all, right? So these are the sequence that you would do that. So Ming's thesis actually mentioned that part. He has a few use cases. He just didn't put that into a paper format. So if you check online, you can just type Ming Liang and then the thesis, the PhD thesis. You'll find that part after the topology generated, how you assign these different components based on the result. Okay.
All right, I sent messages to Sharon and Saga. Hopefully they will type back because they are still here. Now I'm going to move to the next one. I also want to thank Ian for the presentation. So Ian, when you do the forecasting model, you know, there are so many of them. They are LSTM, they are physics informed, they are ResNet, there are also variation of those. So can you give us an overview, for example, your vision on this like a forecasting model, and why did you pick up the two for power system engineers? Because, you know, many people are doing that as well. So it will be very nice to hear about your conclusion or vision.
Yeah, this is a very good question. Actually, this is exactly the reason why we developed the model selection mechanism instead of focusing on any single individual model. Because as you mentioned, we have a lot of models existing like LSTM or some graphical neural network and some more advanced ones. And actually each of them has their pros and cons. So for example, LSTM, as we know, is pretty popular and pretty effective in forecasting the time series. And the graphical convolutional network is more effective in forecasting the system with a graphical network structure and so on. Every model has their advantages and disadvantages. So we cannot use any single model to solve all the forecasting problems, because the forecasting problems are also pretty different with each other. So that's why we developed the model selection framework. So we prepare a lot of candidate models like LSTM and the TCN or SVM and GCN. You can add any model you want into the model pool. And then the key is about the model selection. So once you get the model selection framework and combine with your model pool, and then you can identify the most effective model for different problems. So briefly speaking, we do not focusing on any individual one, and we just focusing on the model selection mechanism. Yeah, if you ask me about my opinion about the forecasting technology, I think it's hard to see which model, you know, there are many advanced ones, and it seems to think the model are becoming more and more complex, right? But it doesn't mean complex model should be better. You should consider your forecasting problem itself. So for example, how many data you have, what's the data granularity? Usually more data means you can use more complex model because it is requires more data to train, right? But if you only have limited data, it's better to use some simplified ones. And also if the data is pretty fluctuating with pretty significant nonlinear features, then probably deep learning model will be better. But if you have a pretty smooth curve, then maybe only a classical, the statistical method will be enough. So the good or bad is you should say it only for a particular problem. Yeah,
Right.
I guess that's my answer.
Okay, so typically hybrid method is the best. I understand that. And then if that's the case, then can you illustrate more about your uniqueness, like your method? Why is it unique that you would like to broadcast to the community here? Is there some additional information other than maybe physics informed, or maybe you extract some special periodic pattern? So can you showcase a little bit about your method, why it's wonderful?
Is this question about the PV forecasting or the load forecasting?
I think for both, or you can pick up one. It's a general question.
Okay, so for the load forecasting one, as I mentioned, I would say our main contribution is the model selection framework in itself instead of any individual model, right? So basically for the load forecasting, as I mentioned, we do not focus on any individual model because we believe there are already pretty enough forecasting tools out there, and there is no best model. And because we always need to tailor the forecasting model and select the best one for a different problem. So that's why we focus on the model selection mechanism instead of any individual model. So in order to build the model selection framework, so we use the meta-learning concept. So more specifically, we designed some feature sets to describe the forecasting problem. For example, what is the data granularity? What is the length of the forecasting horizon? And what is the load level, like the mean value, peak value, or average valley value, something like that. So we can quantify the load forecasting problem. So this is the feature set. And then we also test the model performance for different candidate forecasting models so that we know on what problem which model performs the best. And then we try to construct the mapping from the features of the forecasting task into their best models. So this is how the meta-learning process is established. So during this process, we also did one thing I think we should pay attention in the future is that we also did quite a few tests on the meta-learner, which constructed the mapping from the task feature to the best model. So actually the selection of the meta-learner is another question that it worth identifying because we also have a lot of classifier can be used, right? So this can be another meta-learning problem. So it seems this problem can be endless if we do it, keep going this way. So I think if you ask uniqueness, I think it's mainly the big idea of the framework. So I saw some previous studies on this that's similar to our framework, but I think actually I read a lot of papers before we writing this one, and I think most of them didn't give a rigorous formulation about the meta-learning framework. And based on our framework, you can just repeat the process step by step, so it's easier and more clear. And also we defined quite a few, like over 800 forecasting problem with different features. And the previous study, they usually use like a tenth of forecasting problems. And I think that's not enough to test the performance of the meta-learning framework. So for the PV-free forecasting problem, I think still it's a hybrid framework that includes many different components like the data-driven spatial temporal one and the neighbor selection one and the physics-based model. So we actually, each of them are already studied by the community, right? They are already physics models and spatial temporal forecaster. But we believe, as you mentioned, a better forecasting tool method is always a comprehensive one, or we cannot just rely on any individual one. So we just, if you ask me how to improve the forecasting in the future, I think the key is to try to maximize the value of the data. We just use every data we can use and extract their information and use this information to forecast it into the future. In order to extract the information, we need different methods, maybe the physics model, maybe the data-driven model, maybe some domain knowledge. And we need to find a way to combine them into a final forecasting framework. So I guess that's my answer.
Okay, sounds good. And finally, I want to return to Lin's last part. You talk about the reinforcement learning, and you propose a new two-stage method. Yeah, on stage one, maybe this is like a pre-processing. On stage two, they get more information. They do their control. I want to know for this reinforcement learning, do you need to disturb the system? So that's question number one. And question number two.
Do I need to do what?
Disturb the system. If, for example, you need to learn, right? Even if you use DDPG, you need to ask the system to change maybe the capacitor bank.
We actually
maybe
use continuous training. Our environment will
Mhm.
be every 5 minutes, we have a new set of data, and then you
Mhm.
put them in, right? So your environment is changing all the time.
Right, the environment is changing, but do you, yeah, for example, when the environment is changing, the power engineers will typically regulate the voltages by themselves with some heuristic method. And when you are doing your
In
training,
distribution system, you
Mhm.
don't do that. You usually use automatic control the cap banks. So you only need to model the
Right.
cap bank activity. You don't have
So
a
you
human to
Mhm.
regulate that.
right. That's what I mean by heuristic method. So when you do your training, because reinforcement learning, you need to perturb the system, right? If, for example, when you are trying to get out of the door, you need to perturb which one is the wall. So do you perturb the system or you don't perturb the system? Because that's an online training question, offline training
Oh, you
question.
mean the online training? What we're talking about is offline training right now.
But for
so
offline training, go ahead.
So what we're training is we have a distribution system, right? You have the
Right.
PV is changing, load is changing, right? So we
Right.
run this, each episode, for example, is a, like say, you have a epoch for like say a day or two, right? So you
Mhm.
advance it for these and then you get the results and then you're training like this. So when you say
Mhm.
perturbation, I don't understand what you're talking about because inside this environment, if the PV agent make any action, right? The system will change, right?
So is that
According-
action by you or that action is by the PV itself?
The PV has a control agent. That's the agent that we want to change, right? So the agent will tell you to generate or to absorb power, reactive power,
Mhm.
right? Once you
But
absorb,
that's the policy, right? Policy is designed by you. You perturb the system in order to learn the policy, and then you give the policy to the PV controller. So that's what I mean by perturbing the system, because sometimes we need to get some weird number for the controller to try so that we learn the policy
I
better.
think we use a policy critic method to do the training. So the critic itself is also a neural network, right? So
Right, but you know, neural network can get unrealistic or try something that can go violate the system safety, right?
You can have the word and then the score to design that, right? So if you do something unrealistic and then you can see that voltage limit, you game over, then you will get a large penalty, right?
I see. Okay. All right.
Yeah, we do everything based on, it's like you're putting into a battlefield. So the score you receive, depending on how many enemies you killed, right? And then if you were killed, then you're game over. That's the biggest penalty you could have got, right?
I see. Okay.
Yeah.
All right. Then, yeah, I guess that those are all the questions from the audience and the committee here, including myself. Thank you so much. Thank you for Ian to come over. What we are going to do is we are going to combine the two videos together. I apologize again about the technical issue. And then, yeah, we also get some nice Q&A. Our webinar series task force is trying to do the translation from video recording to the Q&A. So for example, Ian said something about the vision into the future. So we are going to transcribe them into sentences. And then later we are going to put them onto the website. Of course, we will send the link to you so that you can have a look or to see whether you want to change anything. But yeah, basically we want to make it more of a video and like a collection of many Q&As.
Okay.
Do you have any question for us, Professor?
No, thank you for the organization.
Yeah,
Of this,
thank you.
Seminar. Yeah.
All right.
Let
Okay.
us know,
Appreciate your time.
yeah, when you need us to review it, let us know. Thank you very much.
Okay. All right. Thank you. Bye now.
Thanks. Bye.